Our next topic, we're going to take a look back at our Cartesian geometry as opposed to Euclidean geometry. Euclidean geometry named after Euclid, so that's our angles in a triangle add up to 180, those sorts of things. Cartesian geometry named after René Descartes, which is our number plane. Now, a couple of formulas we should be familiar with. The distance formula, basically Pythagoras' theorem. So if we wanted to find the distance, so let's just do a simple example here, between -1,3 and 3,5. Sub into our formula. Look, you don't have to write the formula down as your first step, but it is important that you show the actual substitution. The 5 minus 3 squared plus 3 plus 1 squared. We end up with root 20, which is 2 root 5. So say the distance formula is basically finding the length of the hypotenuse using Pythagoras' theorem. One side would be the difference in the x values, one side of the triangle would be the difference in the y values. Okay, midpoint. There's its formula. So midpoint, as the name suggests, the middle point. Here we're basically averaging the x values and averaging the y values. Again, let's do a simple little example. Average the x values, average the y values, and we get a half 5/2. So as the name suggests, midpoint is average. I talked about Euclidean geometry earlier. There's nothing stopping us using Euclidean geometry to solve Cartesian geometry questions. It's all geometry. So some of the ideas that come from Euclidean geometry are very useful to solving problems in Cartesian geometry. Quadrilaterals, for instance. So remember how we classify quadrilaterals. They're always classified according to the different features. And the more specialized it becomes, the more features they possess. So as we branch down that quadrilateral family until eventually we get to the perfect quadrilateral, the square. So any property that you know about a particular quadrilateral can also be used for any shape that branches into it. So for example, a rhombus, if you know the shapes of rhombus, yes, it will have the properties of a rhombus, but it'll also have the properties of a parallelogram, a trapezium, a kite, and a quadrilateral. So let's have a look at the specific features. A quadrilateral, well, features. Yeah, it's got 4 sides. Yeah, it's got 4 angles. That's pretty much all we know about quadrilaterals. Okay, it branches down to the kite. What do we know about a kite? A kite has pairs of adjacent sides that are equal. Diagonals in a kite are perpendicular. And we've got a formula for an area of a kite, half the product of the diagonals, which you may have thought was the area for a rhombus, but it's actually the formula for the area of a kite. Trapezium, one pair of sides are parallel. And the area for that one, half height, a plus b, sum of the parallel sides. Okay, the trapezium can branch down to the parallelogram. And now we have 2 pairs of parallel sides. Opposite sides in a parallelogram are the same length. Opposite angles in a parallelogram are the same size. And diagonals in a parallelogram will bisect each other. We also have an area formula, base times height, and that's the perpendicular height between a pair of parallel sides. Note, if you had to prove a shape's parallelogram and you only know information about one pair of sides, if you know that pair of sides are both equal and parallel, that's enough to say the shape is a parallelogram. Okay, the rectangle branches off the parallelogram. We get a little bit more specialized because now we know that the angles in the rectangle are 90 degrees. The diagonals now become equal. And we have an area formula, length times breadth. Our rhombus branches from both the kite and the parallelogram. This is why we use the formula for the area of a kite to find the area of a rhombus, because a rhombus is a specialized kite. The additional properties from a parallelogram and kite, we now know that the diagonals will bisect the vertex in a rhombus. Then we get to our perfect quadrilateral. It has all the features of all the quadrilaterals. If we wanted to, we could have an area formula, the side squared, hence the name square. Let's do a problem. We've been given 4 points and they want us to show that this shape is a rhombus. So we need to prove some of the properties of a rhombus here. Well, I know the midpoint of AC. That's 5/2 minus a half. I can find the midpoint of BD, and guess what? It's the same point. So that's telling me that the diagonals bisect each other, and that's enough to say ABCD, we know it's a parallelogram because its diagonals bisect each other. But we want to show it's a rhombus, so we need to get a bit more specialised. The length of CD I can work out, that's 5. The length of AD is also 5. Well, hang on, we have a pair of adjacent sides equal. So it's a rhombus. Oh, a parallelogram, which is also a kite, must be a rhombus. So 7A has got those sorts of coordinate geometry questions in it.